Hello everyone. In today's video, we are going to examine another crypto system called Affine Cipher. We are going to formally define what an Affine Cipher is, and we are going to see a detailed example of Affine Cipher. To get the most out of this video, I hope you are familiar with the following concepts which will be used in this video. So one is modular arithmetic. The second concept is the GCD algorithm. So if you're given two numbers and you are asked to find their GCDs, you know how to do that. If not, hopefully the example that we're going through, I'm going to take a step-by-step approach. Hopefully it makes sense to you. And lastly, how to find multiplicative inverse. So for example, if you're given an element in Z26 and you're asked to find the inverse element of that certain element, you are able to compute that value. So without further ado, we are going to have a look at the definition of Affine Cipher. So we are going to look at the definition of Affine Cipher. Just keep in mind for Affine Cipher, there are 5 components: plaintext, ciphertext, key, encryption function, and a decryption function. Now with this in mind, let X and Y denote the plaintext and ciphertext respectively in Z26. The reason we're working with Z26 is that there are 26 letters in the English alphabet. If you're using another language that has a different number of letters in it, then you use that number, but the idea is the same. We let the scripted letter K denote the set of ordered pairs A and B, both members of Z26, such that the GCD of A and 26 is 1. All this means is that A and 26 are relatively prime to each other, or in other words, they do not share any common prime factors. So with this in mind, let the ordered pair A and B be a member of this scripted letter K. Then the plaintext X can be encrypted by the following equation: y is equal to ax plus b mod 26, and given this ciphertext y, we can decrypt it via the following equation: a inverse times y minus b, where when we write a inverse, we are actually referring to the multiplicative inverse of a in Z26. So now before going over the example, there are some important implications in this definition that are worth going over a little bit deeper. So we're gonna do that first, and then we are going to have a look at an example of Affine Cipher. We just saw the definition of Affine Cipher. It was mentioned that a permissible key is an order A and B such that the GCD of A and 26 is 1. Now, this implies one of the implications, direct implication of this definition is that the key space is finite, and we can find the exact number of keys, and we're just going to do that right now because it might give us a better understanding of the key space. As you can see in the definition, there are no restrictions on B, the second element of the ordered pair, so there are actually 26 distinct elements in Z26, so B can be any one of these elements. And without any problem, there are 26 possible values for B. As for A, there is a restriction. The definition says that the GCD of A and 26 is 1. That means we are interested in the numbers or integers that are relatively prime to 26. And there are 12 of those numbers. But how do we know it's 12? This part is extra material, so if it looks overwhelming, don't worry, but it helps with understanding the key space. Euler phi function is a function that gives us the numbers that are number of integers that are relatively prime to a certain number like 26. So the number of relatively prime integers between 1 to 26 can be found by finding the value of phi of 26. Well, the prime factors of 26 are 2 and 13. So we can write 26 as 2 times 13. And if we know Euler phi function, it's a multiplicative arithmetic function. So we can just write phi of 2 times 13 as phi of 2 times phi of 13. And because 2 and 13 are both prime numbers, we can deduce the numbers that are relatively prime to them just by subtracting 1 from each of them. So 1 is the only number that is relatively prime to 2, and between 1 to 2 actually, and then for 13, between 1 to 13, there are 12 such numbers that are relatively prime. And to finish off, we just multiply these two numbers, 1 by 12, and we get 12. So there are 12 possible values that are relatively prime to 26. That's the conclusion. For your reference, I've included all these possible values. You can go through the list, count them, see there are 12, and if you're interested and if you're familiar with the multiplicative inverse concept, you can justify yourself that there are actually among these elements, there are multiplicative inverses. And lastly, this implies that there are 392 possible keys in total, 12 coming from the first component of the ordered pair A, because there are 12, and then 26 for the second component of the ordered element. There are 26 such elements, so 12 times 26 is 392. To finish off this part, it is worth looking into some examples of key and non-examples. So first we're going to look at the examples. The second component, we actually not concerned at all. Anything that can go into that component, no problem. But the first component, we have to make sure that they're relatively prime. 26, 3, and 17 are actually both in that list of numbers that are relatively prime to 26. And we know that they don't appear in the prime factorization of 26. No problem. There are permissible keys of Affine Cipher. And lastly, we are looking at the non-examples. Again, the second components, we're not concerned at all. Anything can go in there. But the first components, we have 2, 4, and 13. 2 and 13 both appear in the prime factorization of 26. So obviously, their GCD is not going to be equal to 1. As for 4, well, the only prime factor of 4 is 2, so 4 and 26 are sharing a prime factor, namely 2. Therefore, again, the GCD is not equal to 1, and it cannot be a permissible key of Affine Cipher. So now that we got a better understanding of the key space of Affine Cipher, in the next slide, I'm going to justify why the decryption function works. And then after that, we are going to look at our example. So the second part of the definition that we are going to examine right now is the decryption function, which is given by the following equation, A inverse times Y minus B. It may not look like the inverse operation in the first glance. It's very easy to justify yourself that that's actually true, but for the sake of completeness, I'm going to give an argument why this decryption function works. So just to remind ourselves, our encryption in Affine Cipher is given by AX plus B. So going back to this decryption function, we can plug in instead of Y, AX plus B. We get the following equation, and we can see we have ax plus b minus b, so b's cancel out. We get a inverse times a times x. A inverse times a is actually just 1, the identity element, and 1 times x is just simply x. So that's the reason why the decryption function works. For the example that we're going to be going over for Affine Cipher, I've chosen the plain text smile because I'm hoping to bring a smile to your face by in this video since we are learning about Affine Cipher. And for the key, I've chosen the ordered pair 5 and 18. In general, if you're given an ordered pair, it is a good idea to double check whether it satisfies the requirements for being a key or not. In this case, 5 is a relatively prime number to 26, so it satisfies the condition, but it's a good idea to double check that first and make sure it is a permissible key. As with other crypto systems, we usually tend to divide our plain text in and put it in a table like this. And then since we are working with modular arithmetic, we have to map these letters to a number. We have our table on the slide, so we can read off the value. We look at letter S actually at first in that first table, and then we look at the mapping table this time. We find letter S, and we see it corresponds to number 18. And we record number 18 in our table, and we do the same for the remaining values. M correspond to number 12, I correspond to 8, L 11, E 4, so on and so forth. So next we note our encryption function, and before going over the exact values that we're gonna get for our encryption function, it is worth identifying different components. So A in the encryption function refers to the first component of the order pair, which is number 5 in this case. Similarly, B in the encryption function refers to the second component of our key. In this case, it's number 18. And lastly, X in the encryption equation refers to our plain text. So these would be the values that we got for our plain text by reading the values from the table in the bottom of the slide. So for example, number 18, 12, 8, 11, 4 in this case would be the values that we plug in for X. Now that we have identified different components of our encryption function, it is time to actually plug it into the encryption function and see what values they output. So in this case, it would be the values in this row. We're gonna plug them in this equation. So 5 times 18 is 90, 90 plus 18 is 108. So that's the value we'll plug in underneath S in this case. And next we do the same process for all the remaining values. So we plug in 12, 8, 11 for one by one into that equation. Now the next thing that we need to do is if we look at this encryption function, it's in it's interested in the values in mod 26. So we just take these values in mod 26. I've already pre-computed these values, and if we do this, we get 408, and we complete the same process for the remaining values. We get 478. It's actually a divisible number by 26. So 26 times 3 gives you 78. That's why we get 0 there. For 58, we get 6. For 73, we get 21, and so on and so forth. So now at this point, to complete our encryption, we have found the numbers that the ciphertext correspond to in English alphabet. The last step would be to find those letters actually in English alphabet. To do that, we simply going to be using this table here. So we look at, for example, our first element, number 4. We go to this table, we find number 4 here, and it corresponds to the letter E. So we write down letter E underneath 4, and we do the same process for the remaining numbers. So for example, 0 corresponds to letter A, and we complete the same process for the remaining numbers, and we get our ciphertext. As you can see, letters E, A, G, V, M hopefully they don't mean anything to anyone. That's the whole point of cryptography, actually, to come up with ciphertext that is unrecognizable to humans, but there is a meaning behind it if you have the proper key. So there you go. We found our ciphertext, and now in the next part, we are going to inverse this process actually. So we've done the encryption. Now in the next step, we're gonna look at the decryption function, and hopefully we're gonna get the same plain text smile back once again. So this time we're going the reverse direction. We are given a ciphertext, we have a key, and we want to decrypt the message behind it. We remind ourselves of the decryption function, which is given by x is equal to a inverse y times y minus b mod 26. If we look at this function, we have most of the elements that we need. Y is our ciphertext. We have that. B is the second component of the order pair, which is 18, but we don't have A inverse. What we do have is A, which is the first component of the order pair, or number 5. So in the next part, we're gonna look at how we can find the inverse of A, in this case, inverse of 5 in Z26. So if you remember in the very first slide, I mentioned that understanding of multiplicative inverse is a requirement to better understand this tutorial for Affine Cipher. If not, I hope this is a refresher for most of you, or you are familiar with this part, but I'm just gonna give you a quick description of how we can find the multiplicative inverse of 5 in Z26, because actually, as you'll see, using the Euclidean algorithm, there's only one step in the process, so it makes it a lot easier, but that's not the case all the time. So using the Euclidean not the Euclidean geometry, but the Euclidean algorithm, we know 26 is 5 times 5 plus 1, and we can rewrite it and rearrange it so that we can write 1 is equal to 26 times negative 5 times 5. So we just brought 5 times 5 to the other side. That's all we did. And now in the next step, we're just going to look at this equation mod 26. So 1 is equal to negative 5 times 5 mod 26. Actually, the reason that 26 is, disappears is that 26 is actually divisible by 26, obviously. So that's why it disappears in this equation. And we're all pretty much done. This means that the multiplicative inverse of 5 in Z26 is negative 5. And we know negative 5 is congruent to 21 in mod 26. Therefore, we can conclude that the multiplicative inverse of 5 is number 21 in Z26. So again, continuing our process in decrypting the ciphertext, we needed to find the inverse of A in mod 26. In this case, that was 5 that we were interested. And we found out that if A is 5, then the modular inverse of 5 is 21 in Z26. So we record that the modular inverse of 5 is 21 here. And then, as before, we are going to create a table and write down the ciphertext that we have. So letter E goes in the first cell, and the remaining letters A, G, V, and M go in there. And as before, we're going to look at our table, the mapping between English letters and numbers. So E corresponds to number 4, A corresponds to 0, and so on and so forth. We complete the table. Now next, we're going to use a decryption function to find the plaintext. So we record our decryption function one more time here, and plug in the actual values, 21 for A inverse and 18 for B. and we compute the values of these the output of this function once we plug in the values of the ciphertext. So for example, we plug in 4, we get negative 224, and similarly we plug in other values, we record the output of this function one more time, and I've done the calculation for you here. You can see these values, and then the same way in the encryption function that we were interested in these values mod 26, we just compute these values again in mod 26 as well. So we do it for negative 294 mod 26. This value corresponds to 18. Similarly, we do the same process for all the remaining numbers in this table. And as you can see, we get values 12, 8, 11, and 4. Now, again, now that we have the representation of these values in mod 26, we just have to read off the values that they correspond in English alphabet throughout the table that we have on the bottom of the slide. So number 18 corresponds to letter S in English alphabet in this case. And we do the same process for the remaining numbers in our table, read off their values from the table that we have on the bottom of the slide. So for example, number 12 corresponds to letter M, 8 corresponds to letter I, and we do the same process. We look at the plain text that we get using the decryption function that we used, and we see we got our the same plain text that we started originally back once again, and the word is smile. So that's it. We got our plain text back once again, the word smile. And just to give you a recap, we start with the word smile, we use our key, use the encryption function, we get a certain ciphertext, and on the way back to the plain text, we started with the ciphertext, use the decryption function. We had to find the modular inverse of 5 in Z26, and we went through the process as I described. We got our plain text back once again, the same plain text that we start with the word smile. And with this, I hope I brought a big shiny smile to your face. I hope you've enjoyed this video, learned something new about Affine Cipher, and this is it. I hope you've enjoyed this video, and until next time, bye for now.